Today we will be discussing circuits, specifically direct current circuits. The main topics of discussion will be voltage or electrical potential, current, the flow of the charge, the resistance to that flow, and power, or the consumption of energy as the charges flow. Let's begin by discussing voltage. It's oftentimes also referred to as electrical potential or electrical potential energy or electromotive force, EMF. And all of those terms have slight variations, but for the most part refer to the same thing. They all refer to the fact that there is a difference in potential energy acting on a charge at a distance. To look at a specific example, if we take a bar magnet, which I've drawn here, with a negative end and a positive end, and place an electron some distance away from it, because the electron is negative and this end of the magnet is negative, we know that the electron will be pushed in this direction. Or it wants to be pushed in that direction because of the repelling force between the negative end of the magnet and the negative electron. If it were to get pushed further and further, that force would get smaller and smaller because the distance between the two would be greater and greater. Or rather, the electrical potential energy on the electron gets weaker as the distance grows further. Because the electron placed at a distance r away from the negative end of the magnet wants to be pushed or has the potential to be pushed away, and keep in mind it could also be pulled, but in this situation it's just being pushed. Because it wants to be pushed, there is the potential for it to move, or the potential for energy to be consumed. And that's where the term electrical potential comes in. So at each distance, there is this potential energy based on how strong the charges are and how far away from each other there are. So before we get started with any actual values, we need to define our terms and our units. A difference in electrical potential, or the difference in how hard the electron would be pushed from, say, point A to point B, a change in the potential energy of the charge placed there, is equal to the potential energy or change in potential energy from location A to B divided by the total charge. Looking this in terms of units, we have joules for energy per coulomb, or rather a difference in joules at location A to location B divided by 1 coulomb. So 1 volt is equal to 1 joule per every coulomb of charge. Now that we have that, we can go back and look at our specific example with the magnet and the electron. So now, cleaning up our work, now that we've defined our terms for volts, I'm going to replace what our charge of an electron with a 1 coulomb charge for simplicity's sake. Or rather, negative 1 coulomb, so we maintain that negative repelling force or repelling potential energy. Meaning the negative 1 coulomb charge wants to be pushed this way by the negative end of the bar magnet. It has the potential to be pushed that way. That is known as your voltage, is the difference from location A to location B, or the difference of 10 volts of electrical potential to 6 volts of electrical potential on that 1 coulomb charge. Now, before we go any further, it's important to discuss that we're discussing the difference in potential, or rather the difference of 10 volts to 6 volts, and not necessarily positive versus negative. When they were first examining electricity, they realized that they were opposite style charges. And they arbitrarily chose positive and negative because it's an easy opposite that our brains have become accustomed to. Applying this to the circuit we have, the difference between this 10 volt and 6 volt charge is 4 volts. And it wouldn't matter if for some reason it went down to over here 0 volts and negative 2 volts. As you go from 4 volts to 0 volts, you have a difference of 4 volts. And as you go from 4 volts to negative 2 volts, you have a difference of 6 volts. So when I say the difference in electrical potential or voltage, I'm talking about the difference, and you need to think about it as a very long number line and how far it would take to go from one point to another. So to go from 10 volts to negative 2, it would take a difference of 12 volts of electrical potential. Now that we have that down, we can look at specifically how this applies to batteries and wires and light bulbs, aka a simple circuit. Down here I have drawn a 9 volt battery, and it'll send the electrons through the wire, through the battery, and back to the other end. And the way it does this is via a chemical reaction that creates a difference in charge between its two terminals, which we refer to as a positive end and a negative end of the battery. Now, just like before, I don't want you to necessarily think about it as positive and negative numbers, just a difference in electrical potential or a difference in voltage. So the difference between the positive terminal and the negative terminal is 9 volts. And this difference will send any electrons that happen to be residing in the wire from one end to the other, which we'll get into the next section known as current. And when it sends those electrons traveling from one to the other, you end up causing the light bulb to light up as the electrons pass through the bulb and heat the element inside. Thanks for watching, and I'll see you in the next section.